first thing we're going to do is we're going to do a little bit of an exploration. Now, the homework in this unit is still going to use stuff from 7.1. So if you have to go back and review the graphing that we did in 7.1, you're going to want to do that because 7.2 will still have you graph some exponential functions. We're just going to look at one new portion of it. So if you noticed in 7.1, we kind of covered a lot in our notes, and your homework was kind of a minimal amount of that because 7.2 kind of overlaps with it a little bit, okay, with the graphing portion. So do you guys remember this formula right here that's up at the top from when we did Financial Week and we talked about compounding interest? So we've been doing the simple interest equation. So the simple interest equation looks like this, where if you know a rate of increase or decrease per year, you just use this simple formula with a plus or a minus. And then remember what we said if someone starts compounding your money. If I'm giving you a 12% rate per year, then you're just going to put 0.12 here and then calculate how many years. But if I say I'm going to compound that monthly, that means I'm going to take your 12% rate, but I'm going to split it up over 12 months. So all of a sudden your rate looks smaller. But then because I'm splitting it up over 12 months, I have to multiply 12 times however many years that you have there because I'm looking at it all this different time in a year, not just once per each year. And so that's how they kind of came up with this formula that we saw in Financial Week, right? The ends showed up like the number of times that we're compounding it, okay? So what we're going to look at today, and what was interesting as we were doing some of that Financial Week stuff, is as we compounded more, what generally happened to the amount you owed or the amount you would get for your investment. The more they compound, what? The more you owe, right? Or the more you get from your investment, depending on which way it's going, right? So if you invest in a bank, you'd like them to compound more. If you are paying interest on a loan, you would like them to not compound more, right? Okay? So here's the thing, though. We started compounding a lot, right? And we expected it to grow and grow and grow. And if you guys remember, it grew, but it wasn't, at the beginning it was growing, like in kind of leaps. And then all of a sudden it started growing in like little steps. Like it was still a little bit more, but it wasn't that much more. So what we're going to do is we're going to simplify this equation a little bit. We're going to pretend like our principal amount is 1, okay? $1 or whatever, just to make it easy, okay? We're going to call our principal amount 1, and we're going to say that we're leaving it in there for just 1 year so we can see how much interest accrues with this compounding idea. So in making those numbers 1, so if I plug in 1 for P and 1 for T, okay, and I plug in 1 for R, that means someone's giving you 100% as their rate. If you find a savings account with 100% interest rate, call me, okay? But we're just doing this for the simplicity of the numbers, because it doesn't matter what number I put here, it would kind of always work out the same. So I'm choosing ones to make my life simple. If I choose ones for all those things except for n, so I can just look at how does compounding more really affect the numbers, I'm basically plugging n into this formula, right? So this is not a formula. This is what the formula looks like if p was 1, r was 1, and t was 1. Is that okay with everybody? Okay. We're going to use this simpler version and just play around with the number n and see what happens. How much interest is there really on that 1 that was happening before? So you guys have a chart after this in your note guide. And if you don't, you'll just kind of go through and do the same calculations on your own. So basically we have here how many times we're compounding. So we're going to look at all these different situations. And you're going to take that simpler version of the formula where we made P, R, and T all equal to 1. And you're going to plug in the value of n and see what you get. And you're going to write this number out to as many decimal places as you can. So as many as your calculator will give you or as many as you can fit in the spot. Does that make sense? Okay. How many times are you compounding if we say the word semi-annually? 2. Okay. Quarterly? 4. Monthly? 12. Okay. Weekly? 52. Okay. Daily? 365. Okay, we won't do the whole 365 in the quarter, we're just going to go 365. Hourly. How would we figure out hourly? Okay. Yeah, so whatever 365 multiplied by 24 is, that will give me n. Okay. Did we get an answer for that? How many times is that? 8,760? that correct, Lauren? Yeah? Okay. All right. What if we were doing every minute? What would we do? 545,600. Okay, thank you. Sorry. A little bit sick and I don't hear them. Okay, did you just take your 8,760 and multiply it by 60? Yeah. Okay, good. And then if we wanted to do every second, we would multiply this by 60, okay? Which gives us, somebody help me. What does it give us? 153,600. Okay, you guys can confirm 31,536,000. Okay. So go ahead and do this calculation. We've made P, R, and T all equal to 1 to make your life a little bit easier. So it's like you've invested $1, okay, in a savings account that gives you 100% interest. Amazing. For just 1 year. And you're going to see which bank should you go with, the one that compounds yearly, semi-annually, okay, monthly, weekly. What are you going to do? So put in those calculations, and then let's get some answers, and let's look at what we have. Make sure you guys have something like this. I'm doing the same thing. Good my work. For the weekly one, I had slightly different numbers. Did you guys? Or no? Did I just... Yeah? Okay. It's okay. It was real close. I had this. So 2.692596954. Okay. That's okay, Samantha. It's right there. You did all the work for everyone. They can't complain. Okay. So let's see. I just had a difference right here. Like I just had 473. And then for the one before it, right here. Oops. That's not the anniversary. Okay. All right. So let's check out what happened here. Okay, first of all, did your overall expectation get met? Did you expect that the more times you compounded, the more money that would show up? Okay. Now remember, this is an awesome account that has a 100% interest rate, but you've only put in $1, okay? So if they just compound it yearly, your dollar turns into $2. Okay, but if you kept going at this rate, it would be amazing because your $2 would turn into $4, your $4 would turn into 8. Once you hit double digits, you get through those really fast, and once you hit like 100, it's turning into 200, then 400. If people offer to double things for you, it's very good, okay? All right. So then they decide to compound it twice, and you get 2.25. So you guys might be like, 25 cents, no big deal. But you only put in $1. If you had put in $100, that would be $25, not 25 cents that you'd be making right there. Okay. So that's a pretty significant difference when you only put in 1 to get 0.25 extra just because they look at it twice a year instead of once a year. It's kind of a big deal, right? So the amount you get extra here is 0.25 between looking at it once versus twice a year. Then from looking at it twice a year to 4 times a year, it still increases, but not by 0.25 again, only by 0.19-ish, okay? Then from going quarterly to monthly, from looking at it 4 times to 12 times, so looking at it so much more, it does increase, but only by 0.17, okay, 17 cents. Then to go from here to here, okay, from monthly to weekly, they're looking at it from 12 and they're changing the number to 52. That's a pretty big increase in the number of times they're compounding. It does increase, but only by 8 cents. Okay? And then from weekly to daily, it does increase, but only by like 3 cents. And then from daily to hourly, it increases, but not even by a whole cent, like a 0.004-ish. Okay? And then from hourly to minutely, look how much the numbers are different there. You're going from compounding 8,760 times to 525,600 times. I don't know. I feel like I would think that would give me more money. Technically, it does, but by 0.0001-ish. Okay? And then we go from 525,600 to 31,536,000 compounds. And it goes up 0.000001 or something. Okay, so yes, it increased, but does it increase in the way you originally thought would happen? Like more compounding, just like more increasing. It kind of like levels off, right? And it levels off at one specific number, around 2.72-ish. Okay? All right, so go on your calculator. Well, let's ask. We kind of answered these questions, but you can write them into your note guide. So what happened as n increased? Ashley? Good. Okay, the value also increased. So yes, the more times you compounded, the more money you did get. Did the amount change at a constant rate? No. Okay. Is there a limit to how big the amount can get? Does there seem to be a limit that it's reaching? Yes, because once it hit that 2.7 something mark, it didn't seem to change very much. Now the decimal's changing further and further back, but that first part's not changing anymore. So you can look at your number and kind of estimate around what kind of limit you thought that it reached. All right, so on your calculator, there is a button that has an E on it. Okay? Go find that button. Yes. Okay, yeah. So there's actually two. In blue above the division key, you see E. Okay. In blue above the LN key, okay, it's right next to the 4, you see e to the power of x. Those are both the same e. The one above the division sign is just e. The one that says e to the power of x automatically leaves you a place to put an exponent on e. Okay? So go figure out what e is by itself. So either do e to the first power or just do the e, and press enter on your calculator. And go ahead and write that down. Okay, there's a place for it on your note guide. So notice these special numbers that we give names like pi, and now e. E is a number, okay? So easy. They get given a name for a reason, okay? Pi was given the name pi because every time someone measured the distance around an object that was circular, its circumference, and then they measured the diameter, whenever they did the circumference divided by the diameter, no matter which circle they had or how big or how small it was, it always came out to be this same decimal. That decimal must then be special, right? If every circle of every size, you can take its circumference and divide it by its diameter and get this one number, that number must be special. Therefore, we give it a name, pi, okay? If every time you start compounding something, okay, but it kind of reaches a limit, again, that number is a special limit, okay? So this number that you guys saw show up is a special limit, okay? So they call it the natural number because our stuff naturally kind of hits that limit when we're looking at exponential progression. So it's called the natural number, and they use the letter E to describe it, okay? A lot of these are from, like, Greek names. So it's just like pi. It's irrational. It's a never-ending, non-repeating decimal, okay? But here is its value approximated because I ended the decimal. And then, like we saw when we were looking at some of the stuff during Financial Week, we got to a point where we said compounded continuously. And this is the reason why there can be a compounded continuously. Physically, that doesn't seem possible, right? Like, what do you call continuous? What n are you plugging in when you say it's compounded continuously? Well, you don't really have to have a number because at a certain point, we just reach this one number, okay? And so that's why you see E show up in that formula. So this is another interest formula. You would specifically use this if something was compounded continuously in the way that it grows. So A equals P times E to the power of R times T. Okay? So just like in Financial Week, we have a couple of examples here that we could use. Let's just go ahead and do part B. okay, because we've done a lot of this plugging in with this. We don't need as much help with this. If we have a principal of $10,000 at an 8%, okay, annual interest, but we're going to compound it continuously for 10 years. So the minute you see this language, that's your hint that you should be using this formula, because you do have to compound, which means you want to use the formula with n. But then they don't tell you a specific number for n. They say continuously, which means you want to use the formula that has e. Okay? So I'm using this formula. 10,000 is my principal. Okay. Then I have e. That's its own number. Okay? And it's to the power of r times t. So r is an 8%, so it's a 0.08. And that's going to be multiplied by 10 because I'm keeping it in there for 10 years in this instance. So if you guys do that on the calculator and you do it correctly, you should get $22,255.41. 41. Yeah. Good. Is this all right with everybody? So the new formula has E. You would only use it in a situation where either we'll learn about special growth situations that we know work this way, like a continuous compounding, or if it's about money, it will say compounded continuously. Okay? All right, so the only other thing you have to be able to do with E is a number, and it's often used in these exponential circumstances because it came from that formula that was an exponential growing kind of formula. So this is usually the context that you see it. So you will be asked to graph things that have E in them. So at first you might freak out and think like, yeah, right, how do I graph this? But remember, E is a number. Yes, it's an irrational number, but it's about 2.7-ish, right? So look at the equation I'm trying to graph, y equals e to the x. I know it's not exactly 2.7, but if that helps you wrap your head around what you're actually graphing, think of it as 2.7, okay? So is this going to be a growth or decay? Growth, because e is more than 1, okay? Every exponential function has a parent function, which this is a parent function because it's just a number to the power of x. It has that asymptote at y equals 0, and it has that point at 0, 1. So go ahead on your calculator and calculate what is 1 over e, or e to the negative 1 power. You can type it in either way. Savannah, what did you get? Okay, so 0.3 something something. That's as good as I can get with that, right? Okay, and then when I plug in the power of 1, e to the first power is going to be e, okay, which we already have, which is like 2.7 something something something. So there. So here's my parent function. Not that scary, right? Scary because it's the base of e. We're like, what the heck? Oh, even if I remember that that's a number, it's a crazy number, and I feel like I can't do it. But I can. And if they give me something more complicated, like I see right here in part B, I'm just going to take what I drew right there and do some transformations on it. Okay? What transformations am I going to have to do to this parent function to get the graph for part B? Yeah? Good. Because of the negative out here, there's going to be a vertical reflection. So I'll kind of do some of these as we go on my parent function graph. So the vertical reflection is just going to cause this. Okay. What else is there going to be? Good. So there's going to be a vertical translation 3 units up. And vertical translations are the only thing that moves my horizontal asymptote, right? So I basically know that this horizontal asymptote that used to be at 0 is going to now be at 3. Vertical translation went up 3. And then if there was nothing else, if those were the only two, okay, like the 2 wasn't here in front of the e and the plus 1 wasn't there, I would just take these points that were below the asymptote, and I'd put this one below the asymptote, and this one 0.3, whatever, below the asymptote, and this one 2.7. But I've got more stuff I have to do, right? Okay. So what else do I have to do? A vertical stretch, right? So the distances are going to get multiplied by 2. So this distance used to be like a 0.3 below the asymptote. That times 2 is going to make it like a 0.6 below the asymptote. Sorry, a little hard for me to graph on here. This was 1 below the asymptote. A vertical stretch of 2 will make it 1 times 2 is 2 below the asymptote. This was 2.7. 2.7 times 2 is 5.4. Okay, so something close to that. 1, 2, 3, 4, 5.5. Okay, so the vertical stretch is going to end up looking like this. Okay. All right. So now I could take these green dots I do and just draw them up 3, and I would be good. Except for there's one transformation we haven't got yet. More? Good. Okay, because of the plus 1 on the exponent, we have to horizontally translate 1 unit to the left. Okay. So is it okay with you guys, since I've done all the stretching and reflecting, that now if I take all those points and basically move them 1 to the left and up 3, they'll be in the right spot? That's what I didn't do on this graph so far. Okay? So 1 to the left and up 3. I personally like plotting that main point that used to be at 0, 1 first, because then I'm good at understanding where things are around it. I'm not saying you have to do it that way. I'm just saying it's helpful to me sometimes. Okay? So this is new because it used the number e. But are any of the ideas that I used new from graphing exponential functions and performing their transformations? I'll turn off the lights so you guys can see it a little bit better. Okay, so everything went to the left 1, up 3, to the left 1, up 3, to the left 1, up 3. Okay. What would be the domain of this function? All real numbers. Exponential functions have a domain of all real numbers, because there's nothing that we can't plug in from the real numbers that won't function as an exponent. What's the range of this function? Good. Okay, y is less than 3 because our whole graph is happening below the asymptote, and the asymptote boundary is at 3. Okay? So tonight's homework